So here's a demo of the Arduino connected to a LiDAR sensor at the bottom of this. There's the LiDAR sensor, and it's just picking up the distance from the ground, and it's doing this in centimeters. And so when it gets close to the ground, specifically below 30 centimeters, it just changes that to pull up. And then as we get higher off the ground, that distance will change. Sometimes the reflections mess it up a little bit. Even though for the most part the distance to ground readings are mostly accurate, it turns out that comment I made about reflections messing with the LiDAR sensor was a reason I believe the snow on the ground was causing some issues with my readings. So I took it inside just to do a test in a closed environment. One thing I notice looking over this is both times I drop the drone close to the ground, the distance sensor gets thrown off during this rate of descent, which doesn't go against my idea of putting this on there and the thought of triggering some sort of interrupt to say if the drone is close to the ground, it should engage the motors for a few seconds or whatnot. I don't have this implemented, but going forward, it would be something I would be interested in attempting. Going over the code for this project, I'll start with what's going on the Arduino. And the basic requirements for this project dictated that it was using the 9-axis BN0055 accelerometer, but since mine has burnt out or something, it's unable to get any readings, so I used a TF Mini S LiDAR sensor. And getting that to work, I used some resources, which I have cited in the code here. But we'll start with what's going on the Arduino. And so that's on the left side here. I'm using the same software setup as I had for Project 8 and 9, where the Arduino is running FreeRTOS. And I did shift around some of the leads and things on there. So, for instance, digital ports 2 and 3 are now defining a separate serial communication, and that serial communication goes to the LiDAR sensor. And then we have the same, we have 2 tasks. For this one, since it's not being communicated over serial, this transmit task doesn't really get used a lot, but except for debugging when I was going through making sure that the I2C bus is actually picking up, or we're actually sending, well, just to see what distance the LiDAR sensor actually has there. So moving on, we have the serial semaphore, which really has more to do with the reading from the LiDAR sensor. We define the actual registers and values that we're getting back from the LiDAR sensor. It almost kind of acts like its own I2C bus in a way that we're getting from different registers, different values, and there's a high and low integer. You'll see that when I get down there. And for I2C, I referenced, well, because it's given, it's not cited, but the lectures show how to do this I2C setup here, where we have the address that we talk over to the Raspberry Pi, and then what we actually sent. And this, in this case, I'm sending, or at least I'm storing the distance. So we have a high and a low byte for the distance and a high and low for the signal or the strength of that beam. And so I left it as 4, but I don't actually pick up the strength in the readings, just the distance. Okay, so we have our receive and respond for the I2C requests. they're mostly the same here because really it's really the same things going on. We have our data that we transmit, and the only ones we're going to ask for are 0, 0, and 0, 1. So this one is just in case I decided to implement it, but I didn't. Okay, so we start our serial and our LiDAR serial. Both of them are just going to talk at this faster baud rate. It doesn't necessarily matter. We make sure that we can start our semaphores and we create our tasks, the read LiDAR and transmit. Like I said, the transmit task doesn't exactly get used. And this here is referencing the given code um, from the lectures. And now we get down to the meat of what's really going on here. The read LiDAR task, it's going to check a couple times whether or not we have a LiDAR attached. We have a LiDAR connected. We have to make sure that we're not stepping on the serial connection. So we take that semaphore. And then we got to make sure that the packets we're getting are actually like it's not corrupted in any way. So once we make sure that everything is set, we read those values into this array, and we have to do some checking. This was listed in that tutorial. In that resource, it's verifying that all the data matches up as it should, and then this is mostly for transmission to the other task to transmit, but for the most part, we're just going to set our byte arrays that gets transmitted to the Raspberry Pi over I2C. So once those get set, as long as the I2C requests come in, then they'll be ready for response by the Arduino. So here's an example of what that distance calculation kind of looks like. We, for one, we're going to take the serial semaphore, and it's the high multiplied by 256 and the low because we have the differing bytes, place value, and all that. Now, what happens on the Raspberry Pi side? Like usual, we have a service that runs and it picks up in this case, a shell script that's just going to run and manipulate these files and do some requests for the I2C bus. We have an install script that sets that service up when it gets pushed. The previous version, I probably haven't emphasized enough in the past, but this will cause some issues if it's missing because you'll have a ghost service kind of just running in the background, and then your changes don't show up. So here's the real work that happens is pulling in the GPS data the same way as in Project 8, then pulling in the distance, the high and low distant values, parsing those to integers. And so there's our bus for the Arduino, and then the register specifically that we're sending the high and low from. This is for debugging. And then there's our distance calculation, as we saw on the other side, our check just to show that, hey, if our distance is very close to the ground, it's just going to change instead of distance to ground, it'll just say pull up. The thought, like I said, kind of being if this was interfaced with a flight controller, maybe this could trigger some sort of interrupt where if it gets close to the ground, it kind of overrides the motor control for either a number of seconds or some ratio of the distance to the ground or the rate of change to the distance to the ground. So that way it kind of just stabilizes it from smacking into the ground.